Hi, I'm Mrs. Burns and welcome to Chapter 7 and our little lesson on half-life. So there are a couple things that we already know. We already know that isotopes undergo radioactive decay. When they're unstable, they are going to release energy until they come to a stable place in their nucleus. So today we're going to talk about how quickly that occurs. So what is half-life? Half-life basically just measures the rate of that decay. So it's the time it takes for half of the nuclei in a radioactive isotope to decay. So the time it takes for half of the nuclei in a radioactive isotope to decay. So some fun facts about half-life. Radioactive decay, it occurs randomly. Different isotopes of the same element have different half-lives. So for example, carbon-14 versus carbon-12 would have different half-lives. Changes in physical and chemical conditions don't affect the half-life, and we can use half-life to date things from seconds to billions of years. That's how we've dated how old the rocks are in the earth, or how old bones can be. So how does this work exactly? If you have a 100-gram sample of a radioactive isotope and its half-life is 8 minutes, how much do you have after 8 minutes? Well, you started with 100, so in 8 minutes you have half of 100 grams. And we know that half of usually is that secret word meaning times. So half times 100 gives you 50 grams left. Half of 100 is 50. How much of that sample do you have after 16 minutes? So after 8 more minutes, then you're going to have half of 50 equals 25 grams. Well, how much do you have after 24 minutes? Again, after 8 more minutes, you have half of 25 grams equals 12.5 grams. So as you can see here, we've undergone one half-life here, another half-life there, and a third half-life there. So here we have 3 half-lives. All right, let's take a look at this diagram here. It shows how we start with 100% of uranium-235 and how over time that will decay all the way down to here, and it takes millions and millions of years. So in this decay curve, we see that uranium-235 decays over time. Slowly that curved line goes down this way. If you start with 100%, how many years does it take to reduce the sample to 50%? So let's find 50% here on the left, the percent remaining. Follow that over and we get this spot right there with the star. And if we want to know how long that took, we just go down to about, or maybe even like in the middle of that box, like right there. And that is about, I'm going to write about 700 million years. That's a long time for uranium to decrease by half of its nuclei. So 700 million years is a half-life for the uranium-235 decay. Now, sorry that the next question ended up on the other page, but it's right here. The second part of that question was, what percentage of uranium-235 is remaining after 2,400 million years? So if we have 2,024 right here, so if we follow up to the circle and then we dot, 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 dot all the way to the left, we see that there is about 10% remaining still after 2,400 years. Now let's look at this other picture. Here we have that same decay curve in blue. That's the parent. So you might want to label it because it's not very colorful on your sheet. Parent. And then this one here is the daughter isotope. So the parent isotope is the original isotope that is undergoing decay. So we see this decay curve in blue as it swoops down. And then the daughter isotope is the isotope that is being formed because of this decay. So here, this picture is talking about potassium. So we see that potassium, over time, that isotope turns into argon. So if you start with lots of potassium and little argon, then eventually you have equal amounts at the first half-life, and then you start getting more of the daughter isotope than you do the parent isotope. So let's look at a different example. We're going to talk about carbon-14 a bit today. So we see here carbon-14 has a half-life of 5,730 years, and its daughter isotope is nitrogen-14. So we can actually write this as a formula. We have carbon-14. We know carbon has 6 neutrons, and that turns into nitrogen. And that one has 7 neutrons. And the decay that it undergoes is beta decay. So you can write the electron or you can write the beta symbol. So that or this is okay. I don't mind. So that's our little formula. And the C here, this is the parent isotope. And this is the daughter isotope. Oh, my S's kind of got a little bit chopped off there. All right, we can use how much of the parent versus the daughter is present in order to date how old a sample is. Once the parent isotope has undergone one half-life, there is now a 50-50 equal ratio of parent to daughter isotopes. So let's look at this chart here. Carbon-14, again, has a half-life of 5,730 years, and if you start with 200 grams, then how much is left after 4 half-lives? So let's fill in this chart to try to figure it out. We see here that at the start, so time 0 is the start, we have no years have elapsed because we're right at the start. We have 200 that we're starting with. There's no daughter isotope yet. 100% parent, 0% daughter. 100% is 1 as a fraction, 0 of the daughter, and it's 1 to nothing for our ratio. Now let's start to fill this in. After the first half-life, we have undergone 5,730 years because that's how long it takes, we are told, for one half-life. So if we add another 5,730 years, by the second half-life it'll be 11,460 years. And then we will have here, from the start to the first half-life, we have changed our mass of the parent by half. So 200 in half, or divided by 2, is 100 grams. And we need the grams to stay the same. It's just going to change what it is. So that means we're also going to have 100 grams of the daughter isotope, the nitrogen 14, because now we have 100 plus 100 equals 200, and that's the same as the mass that we started with. So now we only have half, so 50% of the parent, and now we only have 50% of, or now we have 50% of the daughter isotope. So the fraction of the parent, now since we have 50 divided by 100 equals, we have a half. The fraction of the daughter, 50 divided by 100 equals a half. And 50-50 is 1-to-1 ratio there. So now let's look at the second half-life. The mass of the parent, 100, has gone down by half, so now we have 50 grams. The daughter has increased that extra 50, so now it's 150 grams. The percentage of the parent goes down by half, so now we have 25%. The percent of the daughter goes up that same amount, so now we have 75%. Now the fraction of the parent is 25 of 100, and that fraction is 1/4. And so you can do one of two ways. Well, you can say 75 divided by 100 gives you 3/4, or you could say that the two fractions has to equal 1 in the end to make one whole. So you could say, well, I know that the remaining here is 3 out of 4 if 1 out of 4 is taken up already. And our ratio we see is 25 to 75. So that as a ratio, if you reduce it to lowest terms, it would be 1 to 3. So we have 2 more half-lives left in this chart, and I'm going to let you complete this for homework, and I'll know that you completed it if I check it and it's filled in next day, and we will go over them together, don't worry. Please come with lots of half-life questions, and we will explore this concept a lot further.